Hello, welcome to part one of a video series on asymptotic approximants. We are just going to jump right in to applying it to an example. Just like playing a new board game, right? You kind of have to play the game to learn the rules. And I figure that's the fastest way to do this. So we'll start by, I'll start by showing how to find some analytic solutions to nonlinear ordinary differential equations using this method, asymptotic approximants, which I'll define later. And we're going to apply it to nonlinear ordinary differential equations, not because they have to be nonlinear, but because usually if it's linear, you already can solve it. So the usefulness of a new method vanishes. Okay, so we'll start with a famous example, the Blasius boundary layer problem, which appears in most undergraduate fluid mechanics textbooks. You can take the Navier-Stokes equations, make some boundary layer approximations, assumptions, cross out a bunch of terms, use a variable transform. You can check out the Wikipedia page and end up with this third order ODE with two conditions that are stacked at 0 and one condition that's infinity. Okay, and this is a characteristic of asymptotic approximates that this is the reason that you would use asymptotic approximates is to find a solution that's accurate in two different places and it merges the two together. So here it's 0 and infinity. And I don't know if it says here. Oh, it doesn't say that there isn't an analytic solution, but a lot of fluid mechanics textbooks do say that. It does say it can be solved numerically, which often implies that there isn't a readily available analytic solution, but I will show you one right now. So let's just copy this over into the Jamboard here. 2f triple prime plus f double prime times f equals 0. And the conditions are f of 0 is 0, f prime of 0 is 0, and f prime of infinity is 1. Okay, so you can see already that it's weird, right? And that it's not an initial value problem. If you want to numerically solve this, you have to use shooting. You have to guess f double prime of 0. And keep on trying different f double prime of 0s until you get to something that at a very large value of the independent variable, some surrogate for infinity, goes to 1. Okay, so for now, what we're going to do is we are going to assume that we know f double prime of 0. And later, probably not this video, but maybe like a part 3 video, we'll talk about how to use the approximate to predict this value. But for now, we're just going to start simple and assume that we know what that is. So it's this value right here, 0.4696, and there's more digits. That's just an approximation. Or 696, dot, 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 dot. And we'll say this is taken from numerics. We will show how to get that later. So at the end, we can't have something that's completely analytical and does not depend on any numerical solution. Okay. So first thing we do is we use the method of power series solution to solve this problem. Typically, textbooks for ordinary differential equations have a chapter on finding power series solutions to differential equations, to ordinary differential equations. But usually the examples are linear. The reason for that is because there is certain identities you need to use for nonlinear ODEs. That said, it's a perfectly fine method for nonlinear ODEs. You just need to know what those identities are, and you can always find them. So first we're gonna get the series solution. So let's say that's the first step. Get a power series solution. Now, usually I make this power series solution to be an expansion about the independent variable equaling 0, or do some variable transform such that that ends up being about 0 in some shifted scale. That just makes things easier to write down, saves space on the paper. But you can, if you want to, you can do the expansion point about any point where information is known. Here it's known as 0 because you have the initial conditions. Okay, so another thing to note is that the independent variable for this problem is eta. So f prime is df d eta. Okay, so to get the power series solution, there's a few. The first step is to assume that you have a power series in the independent variable. Okay. And then what do we need? We need the second derivative, we need the third derivative. So let's go ahead and do that. So I'm just going to go in order here. So f prime is equal to n times a sub n eta n minus 1 f double prime. Let me expand this window, give us some more space. Is n times n minus 1 a sub n eta the n minus 2 f triple prime is n minus 1 n minus 2 a sub n eta to the n minus 3. Now, doing this step 1 might not be important to you right now because maybe you already have the series in the problem you're working with, but I figured I don't know the audience of who's watching this, and so if you start with a differential equation, I just wanted to bridge that gap from differential equation to series. Okay, and so then we're going to put all these in. Okay, so this goes in there. Right. This goes in there. Was it second derivative? And then this goes right there. Okay, so you plug them all in. And what do we end up with? Oh, one more thing. We want all of our etas to be raised to the same power. So why don't we rewrite this a little bit? Okay, so I'm just going to rewrite a few of these things. Skip ahead in this video if you just want to skip to the series and then how to generate the approximant. So f double prime, right? We want to make this eta to the n instead of n minus 2. So we're going to advance every index by 2. So this is going to be n plus 2 and n plus 1 and a sub n plus 2. Right, so f double prime, just adding n plus 2, n plus 1, a sub n plus 2, eta to the n. Okay, and then f triple prime. Right, we're going to add 3. So we have n plus 3, n plus 2, n plus 1. Right. N plus 2, n plus 1, a to the n plus 3, a to the n. Okay. So we put these into the differential equation, which I'm just going to remind myself, right? This was 2 f triple prime plus f double prime f equals 0. So f double prime f equals 0. And you might be saying, this isn't a new method. And also, Blasius himself worked this out a long time ago. Well, um, I'll just say that there's identities being used here that you'll also might use when you generate an approximant. So it's just good practice for using those identities. Okay, so putting these in.